Right, so what we're going over today, gentlemen, I was going to say ladies and gentlemen, but today we're absent any ladies in class. We're going to go over quiz number 5. Quiz number 5? Quiz number 4 in week 5. This was a quiz that we should have actually had last week, but if you remember I gave you a homework quiz to take away, an older quiz, and I've rewritten this new quiz just for today. So we'll work our way through it, and please, lots of questions, because that's the whole idea of the video, to make this revision to go online. Or we might just so question number 1, I might just put this in my hand so I can see what's going on. Question number 1 had 2 voltage sources. Plus, we had a battery here. What I'll do with the video too, I'll put the inset for the question in the video so you can have a look at this in colour. I've got another voltage source here. This was 270 ohms. These are 18 volts. This is 9 volts. And at 9 volts came down into 560 ohms. And of course, in the exam, you're not given the actual values, you're given the colours. And it comes back over to there. So let's just examine what's happening here in this circuit. We've got current leaving this battery, going through that resistor, doing something with that battery, and then, like we saw last week with current branching, come down through each one of those resistors. And the question is asking us, what's the power dissipated in R1? This is R1 here. And we want to know how much power is going to be dissipated in this resistor. But in this circuit we've got 2 voltage sources, and the 2 voltage sources are back to back. So if we think about batteries which are drawn like that with a tab there, and I've got another tab there. This is plus, plus, minus, minus. And that's what I've got. I've got plus, plus. That 9 volts takes away from that 18 volts, 18 minus 9 to leave a total of just 9 volts in the circuit. If the batteries had been the other way around, if the polarity of that had been reversed, that 9 volts would have added to that 18 volts because we would have had the batteries the correct way around, so to say. So knowing then that we've only got 9 volts in the circuit, what do you think the next thing is that we have to do in this circuit to solve it?
You have to find the current.
We've got to find the current ultimately, but how can we find the current? How can we find the current? Full stop.
Well, how to find the current is V over R.
So what about R?
Well, R's already there. R's given to us.
Oh, wait a minute though. We've got one R, we've got another R, we've got another R. Don't we need an R total?
Yes.
Alright, so we need to find R total for this one. How do we go about finding R total? What do you think, Mumwood? You'd go that way? We could do that. So you mean we've got 2 parallel resistors here? Is that how you'd do it? You'd go one on, this is R2, this is R3, one on R2 plus one on R3, and that'll be 1 over that, and that'll equal total, R total?
Yeah.
Is that what you did in your test?
Yeah.
What did you find for the total resistance?
It's 255.534.
255.5 ohms. Very good. Is there another way that somebody else worked out those two, that resistance? Yes.
Product over sum.
Product over sum. I love it. I do this more often than not. Product over sum. So in this case it'd be 470 times 560 divided by 1030, is it? And that will also give us that same value, 255.5 ohms.
It's not 1030.
Not 1030, I beg your pardon, 9...
No, it is.
Yes, it is 1030. Geez, I thought I was losing it there for a minute. You had me worried. But does that get us out of trouble? I said before that we want RT. Is this in fact RT?
No.
Alex, what do you think?
No.
What do we have to do?
You have to get the first resistor.
we've got to get the first resistor, 270 ohms. So we want this value, 255.5, add 270 ohms, 0.5, 5, 12, 3, 5, 525.5. That tallies up with what I've got here. Does everybody agree with that?
I agree.
All right, and then we learned before, the beginning of this, somebody said we've got to work out the current. How do we work out the current? V on R. V on R. I equals V on R. I'll circle that, I love it. We've got a total of 9 volts because we did that and we mapped out how much voltage we had total in the circuit. 9 volts divided by 525.5 equals, I got 17.1 milliamps. All right, I don't see too many people writing. If you didn't get this one right, please take notes. Not going to stick in your head otherwise. You have to make this indelible some way. And the best way to make this indelible is probably to write it down. So get your book and take copious notes, please. There's going to be the video available as well, but hey, the video is just a video, it's not the notes.
So in here, because they were in series, that's why we just added them simply, right?
This one is in series with this parallel combination.
So we added them.
Yes, we simply added them together. We did indeed, to come up with RT. RT 525.5. 17.1 milliamps is what is flowing here. 17.1 milliamps is flowing through that 270 ohm resistor. The circuit said the power dissipated by that 270 ohm resistor, R1, is, and there's various ways that you could have done it. Probably, and this is how I think I did it, I just went I squared times R, because I already had the 17.1 milliamps in my calculator, so then I just pushed the square function and then multiplied it by 270 ohms, because I only want to know the power in that first resistor. Does that make sense? Did anybody use a different power equation than I squared R?
You can use V times I, can't you?
You can use V times I, but you would have had to get the current, multiply it by the resistance to work out the voltage across it first. So there'd be an extra step involved. Not that it's neither here nor there. I mean, you know, whatever does it for you. But to me, it just seemed easier to use this. So don't forget, you can use V squared on R, you can use V times I. They're all going to work okay. And of course, that made the answer 79 milliwatts power dissipation for that resistor. All right, very typical exam questions these. You see them over and over again with just different values and different battery voltages. Don't fall for the battery situation here. We'll go through a PowerPoint to just revise this, review it later on about Kirchhoffs with resistors in circuits and batteries. I've got a good PowerPoint that we'll go through with that. And you've got to look at whether they are aiding or opposing. I'll write those names down here. Aiding or opposing. And of course in this situation they are opposing, they're not aiding. If they were aiding, it'd be like when you put the batteries into your torch. D cell goes in and the little tag on the top facing up, and the next D cell goes in so that the tag faces up on the top of that. They're aiding.
So for I square times R, you times I square to R1 or R total?
R1.
R1?
Because we're only finding the power in R1. We could find the power in the other resistors because the total power for the circuit is equal to the sum of the individual powers in the circuit. So the power on R2 added to the power on R3 added to the power on R1 would equal the total power for the circuit, and the total power for the circuit would be based on the total current times the supply voltage. So that would be 9 volts times the 17.1 milliamps to give us the total power in the circuit. All right, we might go on to question 2. Question 2 is drawn rather differently to that. So unless there's any questions about what I've got there on the board, perhaps we'll move on. Am I okay to rub that off? Yeah. All right.
So I'm assuming the circuit in the second question is different to the circuit in the first question.
Oh, very much so.
I think that's where I did a mistake.
This outside so I don't choke on it. I don't know what's in this stuff, but it certainly makes me gag. Right. Second question. Voltage source. Resistor coming down here, a resistor coming across here, and another resistor coming down here. They join together and that comes back to there. Oh, we had a milliammeter there. Measuring milliamps. And this was R2. And this was R3. And this is R1. And R1 is yellow, purple, brown, which is 470 ohms. R2 is 560 ohms. And I'm guessing this one is 470 again. 470. I sat down in my little graphics package and I drew those resistors. They look a little bit dodgy, but they do the job, especially with the colour printer. Makes it nice to look at. 24 volts plus. 24 volts. There's going to be current flowing that way, conventional current. All right, what do we have to do? I haven't even looked at the question yet. Maybe I should look at the question. The total resistance the battery sees is, well, hey, that's probably something I was going to do first anyway, because I've told you before, a lot of these questions, when I do them, I don't even read the question. I look at the circuit and then I start doing things with the circuit. I just think logically about the circuit and I go, I've got a few resistors there in series, parallel, what can I do? And I work out the total resistance, and after I've done that, that's when I probably look at the question. So if I'd gone ahead and done that, I would have already worked out the total resistance. Now, the resistance the battery sees, well, it's looking into this circuit and straight away it sees a 470 ohm. But what about these resistors here? What about these? Let's draw a sausage around that.
Well, we're skipping the one in the middle.
Why are we skipping the one in the middle? We're not, because the battery sees that, but it also sees that in P,
That's not parallel.
in parallel.
That can't be parallel, sir.
I'm sorry?
That can't be parallel. That's a series.
Oh, no. These in the red sausage, they're in series.
Yeah.
But that red sausage is in parallel with that. Let's just now, I do know, because even though I learnt this stuff 40 years ago, I do know this gets confusing, and let's just redraw it. Oh, look at that. We've redrawn it. Here's R3, here's R1, and here's R2. Ooh, does that make more sense now?
A lot more sense.
Can you see that they are in parallel with that? But you can't say R1 by itself's in parallel with that. You can't say R2 by itself's in parallel with that. It's the red sausage again in parallel with that. So what have we got to do here?
Make them both one resistor, theoretically.
So Matthew, what did you do first?
Just add them both together.
So R1 plus R2. So that was 470 plus 560. What did we say? That was 1030, wasn't it?
Yep.
1030. And then what was the next step? That's only what's in the red sausage. What comes next?
Well, now it's parallel.
Now it's parallel.
Yeah.
So,
Product over sum.
Omar, do you agree?
Yeah.
So what do I do?
Yeah, product over sum.
Product over sum. All right, tell me what to put into the product over sum.
1030 over,
Oh, I think you need something else first.
times 470.
Times 470 divided by 1030, add 470. Oh, how much is that? 1500, is it? So that's something over 1500. It's 1500. 1030 times 470.
Yes.
Last time I got you guys to give me some answers, I finished up making big mistakes here, didn't I? 1030 times 470. Tell me what you got and I'll tell you if it matches what I got.
484,100.
Yeah, good. Don't do what you did to me last week. You know that? Those of you that weren't here yesterday, I made a comment in class that I put together some video footage based on that board work. Remember I was going to erase the board in the afternoon? I made that quick video. And when I went home and did the edits on the video, I went, hang on, that doesn't add up. And it was the answers that you guys had given me earlier in the day. And none of you picked it. So don't do that to me again. 484,100 divided by 1500, 322.7. 322.7, and that is RT. And that's what the battery is seeing across there. All right, so if we redraw that, battery, resistor, plus, minus, 322.7. And I haven't used blue today. Blue doesn't come out too well on the videos, but I'll use a blue one around there. There you go. That's the answer to that question. So it was B. B was the closest one at 323 ohms.
So
Yes.
to cut you out. Just to clarify, the series and the parallel aspect of it. So that, because the series, the resistors on the top, and in conjunction with the one on the right hand side,
Yes.
does that make it a series, not a parallel?
Okay, think about it this way. The current comes along. If I don't drop my calculator, the current comes along here, and some current comes down here, and some current keeps coming along here, like that. So this is branch 1, B1, and this is branch 2. Branch current. So branch 2 goes through the 470 and through the 560 in series. Right? Make more sense?
Yes.
2 branch currents based on last week's parallel series work. All right. Am I okay to go on to question 3?
If you found a mistake, I can work out the whole thing. All about the branch.
Good to rub it out? No objections? All good?
So I can do this whole exam right now, just by you clarifying that, and I reckon I'll get it 100%.
Well, that's the whole idea of me going through it and doing like the gala performance, because I want you to be able to do this stuff. It's so important, because everything else that we do builds on this. And it's like a house. If the footings for the house are no good, the rest of the house is going to fall down. So, you know, you've got to sort of get that part right. Let's put that outside. I'll leave that door open a bit even, maybe. Choke on that stuff. I dread to think what's in it. We're flying through it. No, we're not. Question 3. Blue's not going to cut it for me. All right.
He has the same resistors as
Same deal as before, isn't it?
Yeah.
So I probably could have left that drawn up. And we've got a current meter there still, haven't we? Yes. MA, and this is 560. 470, and did we change that? No, we didn't. 470. And we've got the same battery, 24 volts. 24 volts. The current meter will read. The current on meter is A, B, C, D. A, B, C, D. All right, well, here's our meter. We need to know how much current is flowing in that branch. This is just like I said in the last question, the branch. We've got current coming from the battery and the current splits. B1, branch 1 comes down here. Branch 2 comes through here and keeps on coming down through there. Branch 2 current. Well, you know, these are independent currents because they're in parallel. That's why the 470 ohm has its own current, 24 volts divided by 470, and these ones have their own current, which is 24 volts divided by the sum of the two. So again, let's put a bit of a sausage around these. 1030 ohms, so I equals 24 divided by 1030, and I came up with 23.3 milliamps. And if you did, you got that one right too. So 23.3 milliamps. A fairly easy one based on the work that we did on question 2. All right, any questions about that? In parallel, each branch has the same voltage across it, but it has a different current flowing through it, called branch currents.
So, sir, it's the meter is reading only the current of these two,
Yes.
and because it's parallel with another one, it's same.
No. The meter is only reading the branch 2 current because the branch 2 current has to come along through the meter and back out. And what we have here, we have another node, and Kirchhoff's current rule says that the currents flowing into the node have to equal the currents flowing out of the node. So branch current 1 adds to branch current 2 to come back here. What would branch current 1 be? Just work it out quickly. It'd be 24 volts divided by 470. 24 divided by 470 equals 51 milliamps. B1, 51 milliamps. So I total is equal to branch current 1 plus branch current 2, 51 milliamps plus 23. We can squeeze that in. 23.3, and what's that? 74.3 milliamps. And you'll find that if you get R total by getting the 1030, put it in parallel with 470, divide that into 24 volts, you'll get 74.3 milliamps, which is the total. Starting to make more sense?
Yeah.
All right, that's good. That's what I like to hear.
To answer the next question, ready to.
Have I answered the next question already?
What was the next question?
That was the next question. The total current flowing in this circuit is. And yeah, 74.3. And what is the total resistance? R total here, and this is what the battery sees. So BAT sees R total, and R total is 1030 in parallel with.
We've already done the total resistance as well as question 2.
Yeah, that's the same as question 2, and that's 323 ohms. 23 ohms, and if you go 24 volts divided by 323 ohms, that will equal 74.3 milliamps. Check it on your calculator. Is it right?
Wait, sir, I'm confused. RT, what you do after RT? RT equals for what? What are you trying to find there?
323 ohms. That resistance in parallel with those, so that's what the battery's seeing.
Yeah.
It's looking into the circuit seeing 323. So I'm saying, how much is IT? IT is going to be based on that, and if we get our 24 divided by the total resistance, 24 divided by 323 equals 74.3 milliamps. Now I've confused you again, haven't I? Why? Because I said that branch current plus that branch current has to equal the total current in the
that's
circuit.
understandable. I'm just confused of why you wrote the RT there and the 1000.
Because I've moved on to question 4, like you said, it's the same as question 4. So question 4 there, you could do it based on the total resistance. And in fact, on my answer paper, I simply looked back up to question 2, like Matthew just said, and I said, well, that was 322.7, bang, brought it over there, put a circle around it to remind me what I'm doing, and then I worked out the total current that way. So you could have worked out the other branch current, added your 2 branch currents together, or you could do it based on the total. That's what I did when I answered the question. Are we good to move on? These come thick and fast.